Hello everyone, welcome to the tutorial on explainable AI as part of the course, and this is Devarpan. I am a PhD student at IISc. Let's go through couple of demonstrations of different explainable AI methods in this tutorial that are covered as part of the course, and the theory part and understanding part of it might have been covered. So the purpose of this tutorial is to go through couple of demonstrations and provide you with starter code so that you can further experiment on it and work on it, and also you can understand those theories better. What is explainable AI and why do we need explanations? Let's recall it a bit. So the modern deep neural networks, especially the CNNs, transformers and others, they achieve extremely high accuracy on tasks like image classification, speech recognition, natural language processing and so on, right? However, they are often treated as black boxes because they are really sophisticated, layered non-linear activations and functions, which leads to a really non-transparent mapping from the input to the output. So you don't really know what is happening inside, although you get high accuracy. So it's important to provide explanations and transparency about the decision making process, because in different safety critical scenarios like medicine, biomedical, other applications, autonomous driving, finance and so on, so they need a explanation behind a decision that is being made. So we see the input, that is image, text and others. We see the output, image, that is class level or probability, but we do not see why the model made that prediction. So for many real world application, this is not enough. We may need to answer questions like which parts of the image caused the model to predict say pneumonia, right? Is the model looking at the tumor or any unrelated artifact, some spurious correlation? Or can a domain expert verify that the model's reasoning is sensible and others, right? This motivates the field of explainable AI. So what is explainable AI? It refers to a family of methods designed to interpret and understand those model predictions. These methods aim to provide human interpretable explanations, that is, they generally try to attribute some features that are responsible for making that particular prediction to the input space, so that you can look at those particular dimension of the input and see if those features are supposed to be at least responsible or critical while making that decision. So identify important features that influence the prediction and reveal spurious correlation if the model have any, and improve trust, transparency and debuggability of the AI system in case they go wrong, or they are focusing on some features that are not supposed to be focused on. For example, while classifying doctor versus nurse, because historical data has more male as doctors and more females as nurse, if a model while learning will learn from the data, so it has a tendency to put some focus on the gender attributes at least while classifying the doctor or versus the nurse. This you would not want to happen, like effect of historical bias. So once explainable AI points you to the fact that a particular model is focusing on some attributes which is evident from the historical bias but should not be focused on and unfair, you can of course work on the model building and model building and creation and training algorithm so that such biases don't come. So where is the model looking? Such methods like class activation maps, Grad-cam, Grad-cam plus and others. And what local changes matter the most? You use methods like Occlusion, shap, lime and others. So they have different algorithms that we will be talking about. So coming to a motivating example, we will take a single example and walk through the entire thing. So suppose we give an ImageNet classifier, this image, a dog sitting on a grassy field, what the model predicts is the question, and why the decision is being made, we will try to probe into that. First let's come to the implementation part. First we make the necessary imports and installations. Let's go ahead. Then we make those a few more imports and call the device equal to CUDA so that the GPU is getting used for model prediction and others. Now Now we load the ResNet 50 model, calling the weights and then call the model and put the model into eval mode, so that the gradients are not computed and GPU usage is limited, right. Then we also create the pre-processing function and also create the levels. So we take an image of two dogs that are sitting on grass, and we load that particular image and show it, demonstrate here. This is the image we will be working on. Now the first question is what the ResNet 50 model, which is primarily trained on object classification. So how it predicts this image to be. So we prepare the image and predict the probabilities and logits, and then given that particular input tensor, how it will predict it to be, right. So what is the top prediction and what is the associated probability. So that ResNet 50 model predicts this image to be a golden retriever with high probability of 0.543 among 1000 classes. So it's pretty confident that this particular image is, the dog is golden retriever. Okay. So now we will particularly dive into the XAI methods and try to see what that particular model of ResNet 50 so confidently telling this particular image to be a golden retriever, and what are the different regions of the image that it is focusing on to predict that. Coming to the first method, which is called occlusion, let us recap it a bit. What is occlusion? Occlusion sensitivity is one of the simplest and most intuitive explainability method. So if I hide some part of the image, does the model's confidence of that class go down, right? So the idea is take the original image, slide a small patch or window over the image, and for each patch location replace the region with a baseline value, which is gray or 0. So you are essentially removing small regions from the image slowly by sliding a window and replacing it with a base value, blunt value like gray or black color, right. And run the model again and again and measure what is the target class probability that is changing. Okay. So if hiding a region causes a large drop in the target probability, that region is considered to be important for that prediction. Okay. So particular, when you are replacing this value by a bloody or black color, the regions for which when you erase them down, then if a particular model's class probability is going down, then for that particular class, that region was important for the model to predict that particular class. So so this is a model agnostic method again, because you are just using the model and not looking at the model's internal details, right. It was ResNet 18 or ResNet 50 or some other network, it doesn't really matter to you. The method applies universally to all the models. Yeah, I have also noted down couple of pros and cons which you can go through. Now in the notebook, what we will try to show is how occlusion is working. So we first load the model and also load the particular image, and then we also define the target, which is to be the top index, right. Then for occlusion parameters, we define couple of things like what should be the dimension of the sliding window, what should be the target index, and what should be the sliding window step. So this particular window shape strides using this dimension throughout the image, right. Now if you aggregate over the channels, because there will be 3 channel, because this is a RGB image, right, and then you can normalize for the visualization purpose. So this is the so left hand side was the original image and right hand side is the explanation generated by occlusion for the ResNet 50 model, which tries to highlight the regions in the input image that ResNet 50 focuses to call this particular image as a golden retriever. So you can see some so red means high and deep blue means low focus. So high focus was being put on the on that dog face, right. So although not very precise, so this essentially tells you that the model is kind of looking at least at the correct region to call it a golden retriever. So then we come to the next method, which is called integrated gradients. Integrated gradients, what it does, it starts with a 0 image or blurry image, then it slowly goes towards the original image. So there is a path from that black baseline, completely black image, which is like baseline, to the original image in an incremental step. you keep adding color slowly and with higher and higher intensity, and finally it becomes the original image. So this is called the path integral, and along that path integral, if you integrate the gradients, they show mathematically that it becomes the explanation. That is only highlighted here. So this is the path integral I was talking about, and for the image, and this, in this case you cannot have a continuous integration, so it is converted to a discrete version of it, discrete sum. So in this notebook we implement the integrated gradients again. We take the integrated gradients import, and we define that baseline image I was talking about, which is like torch dot zeros and should be of same shape as the input image, right? And then we also find the attributes associated with the integrated gradient method. What is the number of steps that connect that baseline image to that original image? You can define that, and you have to also tell what is the target index, which is the golden retriever class's associated index, and followed by a couple of normalization and all. You can compute you can visualize that attribution. So which is shown here at the right hand side. You can see integrated gradients is very precise as compared to the previous occlusion method, right? It is focusing on that dog particularly, and it is showing you really that the regions that it is focusing on and shape that it is focusing on, and a lot of attribution is coming to on the dogs, right? So the model seems to be looking at the dogs to call it golden retriever, which is a good sign. Yeah. Coming to guided backpropagation, what is guided backpropagation? It is a gradient based visualization technique again that produces a sharp detailed saliency maps for a model's prediction. So it modifies the backward pass of ReLU activations so that only positive gradients passing through the positive activation are allowed to flow back. This kind of guides the backpropagation process and removes the noisy and negative gradients. So highlight only those input pixels that positively and strongly support the activation of neurons leading to the target class, right? So how is it different from normal gradient? So for a normal network, forward pass is ReLU, which is max of 0 and Z. Backward pass is gradients are passed back whether the forward activation is positive. But in guided backprop, the forward is same as ReLU, however the backward is modified. So gradient are passed back only if the forward activation is positive, which was also there in the previous case. However, the backward gradient is also positive, which is something really interesting, right? So the negative gradients are zeroed out during backpropagation using ReLUs. This leads to saliency maps that are sharper and more edge focused than the raw gradients, and the visualizations that look like edge drawings of the object the network cares about. Okay, so yeah, that's I think the one of the fundamental parts, and yeah, I have also noted down the pros and cons of this particular method, and then let's now implement it. Once you call this guided backprop using the library functions, you can load the input and also call the attribution, right? And then normalize it to visualize. Here is the visualization of the explanation using guided backprop method of that original image. So what you can see is it's very sharp. I mean, integrated gradients was also sharp, whereas that such precision was missing from the occlusion method, right? So what you see is it is really producing sharp explanations, and a lot of focus is put on the face of the dogs, which is a good sign, because to really tell a particular dog class over other possible dog classes, most of the probably facial features are mattering, so it's really putting focus on them. Right. Now we again come back to another method. We need to modify a couple of imports because different NumPy versions are required for different methods. Once we do that exercise, we come to Grad-cam. What is Grad-cam? So class activation maps are essentially the activation maps of the CNN based networks that is extracted. So those class activation maps, when weighted using the gradients, create an explanation which are mathematically shown in the Grad-cam paper. So that's why this particular method is called Grad-cam. So it's only applicable for CNN based vision models, whereas the previous methods we have already talked about, they didn't really put any condition or constraint on the architecture of the black box network that is getting used. So in this case, Grad-cam is only applicable to CNNs. That's a limitation. However, it provides much holistic and all-round explanations as compared to those previous methods that we will see now. So the early layers of a CNN based network captured the low level features with high spatial resolution. So the deeper layers like last convolution block and others, they capture high level semantic features and object parts with coarser spatial resolution. Right. So the Grad-cam uses one of these deep convolutional layers because it features its feature map still preserves spatial layout. Its channels encode semantic concepts relevant to the prediction. So this makes Grad-cam heat maps localization friendly and class specific, very much class specific, right. So how does this Grad-cam work? Let AK be the kth feature map or activation map from the chosen convolutional layer, YC is the score of class C, and Z be the number of spatial locations in AK. Compute the gradients of the target class score with respect to each feature map as del YC del activation map, and finally the global average pooling is applied on these gradients over the spatial dimensions to get a weight for each channel. So alpha kc is the weight, which is kind of normalization of the gradient of these feature maps. So form a weighted combination and that becomes your and apply ReLU, so that becomes your explanation. And then you can upsample this heat map because it's of reduced size as compared to the original image. So you can upsample it so that the dimension becomes same as the image. How you visualize? We have also noted down the pros and cons that we have already talked about. So now let's implement it. So because this is so much specific about CNN architecture and model specifics, you have to mention really the layer number from where you want to pull your class activation maps. So for example, we will be using layer 4 for that particular ResNet 50 network. Right. So the target layers you have to mention and then call the Grad-cam explainer. So you have to, what you have to provide is the model, that is ResNet 50, and also you have to provide which are the target layers from which you want to pull those activation maps from, and you need to mention the targets. Then you want to convert it probably to grayscale because you want a single map, not an explanation for every layer. Okay. Once that is done, you can work on the visualization and others to finally get this. Now look at it's much more intuitive and not so dotted and pixelated, right. So this explanation is much more holistic and very aligned with the human feature. So whenever we are detecting this particular dog to be probably golden retriever, we are not particularly looking at a pixel level, we are looking at a much broader level and overall the dog, right. So CAM actually aligns itself with such kind of visualization, and looking at this explanation, okay, so it's more or less looking at the dog region. Maybe what exact pixels it's looking at doesn't make much of a sense to you because we don't really look at that level, right. So this gives much more pleasing explanations and human interpretable explanations. Then what came is like Grad-cam plus, which was a further improvement over Grad-cam. So the Grad-cam had couple of limitations which were overcome by Grad-cam plus, and if you look at the explanation, it is of the CAM type, like it gives similar type of explanations, but it leads to even little more precise and little more correct explanations, which may not be for this particular example visually that much differentiable, but qualitatively and quantitatively people have shown on a large set of images it tends to give a little more precise explanations. Finally, we come to last two methods, which is like LIME, local interpretable model agnostic explanations, and also SAP. So LIME and SAP are methods which are again model agnostic. They are not of CAMS types, but where they are unique from those earlier three methods that we talked about. If you remember, we initially talked about occlusion, integrated gradients, and guided backpropagation. So these three methods are not constraining the model to be a CNN type. However, they were using the gradient access through the model, right? Then came the CAM family like CAM, Grad-cam, Grad-cam plus plus. They were also using the gradients, but they were also putting the constraint that the model you are trying to explain has to be a CNN type. Okay, so that's CAM family are more restrictive. Now we come to the most generic setting where you have almost no constraint in it. So you don't even need the gradients like occlusion, integrated gradients, and guided backprop. They were using gradients but had no constraints on the architecture, but we removed that gradient constraint also. LIME and SAP are methods which only rely on input output access of the model. So you can throw me out any model, given an input, that model gives some response, you should give me that access. So I want to use that access many times, but I don't even need the gradient to be passed through that model. So this is a lot of improvement in terms of these constants, because often a time you don't have model which are differentiable from output to the input, like a combination of models, like a logic based model, they are not always differentiable, right? So only LIME and SAP will be able to work on that. However, when you have specific settings like you have gradient access and also CNN type, then you should use CAMs because they will be giving you the best results. So it's all about wide generalizability versus having constants and then providing better explanations. So LIME and SAP come to that setting where it's the most generic setting. What they rely on is that essentially they create for that particular input. Let's say for this particular image, they transform that image into lots of transformed images like masked out versions, contrast enhanced, pixelated versions, and they pass all those perturbations through the model and they get class weights corresponding to different superpixels, we call it. The superpixels are essentially combination of pixels that make a particular sense in terms of broad features like the grass, the flowers. A flower is not a single pixel, a combination of pixel, but overall that combination of pixel makes it a flower. A dog is like that, face of the dog is like that, leg of the dog is like that. So over these superpixels, they perturb these superpixels and get all the responses from the model for all these transformations. From this set of outputs and a set of inputs and set of outputs, it learns a classifier, linear classifier, the LIME model, which gives weights corresponding to different superpixels. So you get to know essentially that which part of the image are important over others. Because you need a lot of transformations of the input and a lot of passes through the model, this tends to again little more, significantly more compute complexity. So I provided the codes for both the methods. However, they tend to take little more GPU memory and little more, significantly more compute time. So you can run it with larger batch size if you have GPUs available, or you can run it in Colab but with a little long runtime. So I provided codes for LIME and SAP both, which you can run and visualize. They are little not that precise like CAMS and others, but they are the most generic methods as I talked about. I'll make this notebook available through the course, and hope it gives you a basic understanding and working principles of these models and demos which you can head start and keep further experimenting with. That was a starter for this starter demos for this part. Hope this was helpful, and yeah, thank you.